Welcome once more to our video tutorial. This time we're going to look at basic logic gates. The presenter is still me, Chigomana MD. Logic gates diagrams. Students, you will understand that digital systems are said to be constructed by using logic gates. Now, what are these digital systems? If you can check how a cell phone, if you can check the content of a cell phone, you check the motherboard of a computer, you check the motherboard of a digital watch, you check most of electronic circuits, you see a lot of components there. Now these components in design of digital systems, we call them logic gates. Now these digital systems are constructed by using logic gates. Now these gates are the following. We have the AND gate, the OR gate, the NOT gate, the NAND gate, the NOR gate, the XOR gate. This one can also be written as XOR, and the XNOR gate, which can be written as XNOR. Let me repeat this. These gates are the AND gates, the OR gate, the NOT gate, the NAND gate, the NOR gate, the XOR gate, and the XNOR gate. Right, a circuit like this, the circuit like this that you see on screen is an example of circuit built using a logic gates. Now, when we talk of logic gates, you will find that each component here, there is a built-in reasoning inside it that is doing a specific function. Now such is achieved by gates. You can find that inside this integrated circuit IC, there is there are gates. In general, when we talk of gates, we are talking of components. But inside these components, that is where the reasoning is embedded. That is where the reasoning is built. So that is what we mean when we say gates. So gates are built in, they are built in these components, so that this circuit can reason whatever it is supposed to reason. Right, now let us continue. Right, at this point in time, we are going to look at different gates and try to define them, where they are used, what type of truth table, and the different illustration when it comes to gates. Right, the first gate that we are going to look at is the AND gate. Now, what is the AND gate? Let us try to define it. The AND gate is a logic device that has two or more inputs and one output. Let me repeat this for the sake of effect. The AND gate is a logic device that has two or more inputs and one output. Right, this is the schematic symbol. This is the schematic diagram of a 3-input AND gate that is shown above. Right. Another thing that you must understand about the AND gate is that the AND gate produces a logic 1. In other words, the output of an AND gate is 1, and its output only when all of the inputs are high. In other words, the AND gate produces a 1. In other words, the AND gate is true only when all of the inputs are high. A logic low state is produced when one or more of the inputs are low. In other words, if in an AND gate it is compulsory that all the inputs, in other words, all the inputs must be high. In other words, all the inputs must be 1 for the AND gate to produce a high output. Now, in order to produce a low output, what we have to do is to make, what must be done is that one of the inputs must be low. In other words, one of the inputs must be false, or you can represent it by a 1. Therefore, what you're gonna have is to get a low output. Now let us go to the truth table. Now this is the truth table of the AND gate. This is the truth table of the AND gate. Now I'm going to place the cursor over each row of the truth table to observe changes in input. Now what is going to happen is that you must be checking what is happening here as I go over each row. Now if you check here, if my mouse is on it's on the first row, if you check on the diagram, you see that the output is low. In other words, the output is it's 0. Right? Even when you check here, the output is still 0, output 0, output 0. In other words, the output is low, 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 low. The only place where, if you are using the AND gate, the only place where you see that the output is high is when all the inputs are high. In other words, in order to produce a high output when using the AND gate, you must make sure that all the inputs are high. In other words, all the inputs are 1, 1, 1, 1. That is true, 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 true. Right. One other thing is that you must be able to draw the diagram. You must be able to draw the diagram of an AND gate. Now this is the diagram of an AND gate. So this one has 3 inputs. So if you are using 2 inputs, in other words, it was going to be A and B. Right, let us go to the illustration. Now, the illustration that we can use here for the AND gates, we'll take 3 switches. The 3 switches are labeled A, B, and C. And these A, B, and C are used to represent the inputs. In other words, here is A, B, and C. It's 3 switches, A, B, and C. They are representing the inputs. And a light bulb labeled X is used to represent the output. Right. All these switches are open. Now an open switch represents a logic 0. An open switch represents a logic 0. And a closed switch represents a logic 1. Is that clear with you? Now let me repeat. An open switch like this one represents the logic 0. And a closed switch represents a logic 1. Now when the light bulb is on, it represents a logic 1. And when it is off, it represents a logic 0. Now the only time the light bulb is on is when switch A is closed and switch B is closed and switch C is closed. Remember we said that for the AND gate to produce a high output, then all the inputs must be high. By high we mean all the inputs must be 1 in order to produce a 1 at the end, as the output. Now the only time, let me repeat this. Now the only time the light bulb is on is when the switch A is closed and switch B is closed and switch C is closed. Now let us go to Boolean equation. Now the AND gate operation can also be expressed by a Boolean algebra equation. Now for the 3-input AND gate just described some time ago, the equation is x is equals to a, b, c. Now the symbol for AND operation is a center dot. In other words, when we're busy doing expressions, the symbol for an AND operation is a center dot. Remember, I've given you other symbols which you also must know. Now, this symbol does not mean multiplication. The dot, the center dot, doesn't mean multiplication. This equation reads x equals to a and b and c. In other words, x equals a and b and c, which simply means that the output of the gate is a logic 1 when a and b and c inputs are all in their one state. Right, let us look at where can electronics experts use this where can they use these AND gates? Right, an AND gate operation can be used to drill a machine part. Let me repeat this. In the example that we're going to have here, an AND gate operation is used to drill a machine part. Notice that the AND gate circuit on this drill press provides a safety feature which prevents the operator from placing a hand between the drill bit and stock. Now, to operate, the stock is detected by a sensor and both buttons must be pushed simultaneously to activate the drill. Now, let us try to view. In other words, in order for the drill to start operating, both switches must be on. In other words, both switches must be closed. Now, this is an example of an AND gate. Now, this is the sensor. This is the sensor part. In other words, when the user presses down this button, now the machine is not going to work. But if the user presses both buttons, then the sensor part is going to sense that there is a piece of metal that needs to be drilled. Now, look, when these buttons, both of these buttons are open, in other words, when both of these buttons are low, in other words, when both these buttons are 0, you see a 0 output here. Now, let us view this animation, and then we'll take it from there. Right, can you see? Now, what is going to happen here? The user presses one switch, one button, and then the other button. Then the drill start working. That is an example of an AND operator an AND gates in real life situation. In other words, to sum up, the AND gate must be both inputs must be high in order for the AND gate to produce a high output. That is why both switches were pressed. Now, if you can press only one switch, it was not gonna work. Alright, that is all what I have for you when it comes to the AND gate. Now, let us go and look at another gate. Right, let us go and look at another gate. Now, this other gate is what we call the OR gate. Alright, the OR gate is a logic device that has 2 or more inputs and 1 output. Let me repeat this for the sake of effect. The OR gate is a logic device that has 2 or more inputs and 1 output. Now, this one has 3 outputs and 1 output. Now, this is the schematic symbol for a 3-input OR gate. The OR gate produces a logic 1. I want you to understand this. The OR gate produces a logic 1 when one or more of its inputs are high. A logic 0 is produced only when all of the inputs are low. Let me repeat this for the sake of effect, so that you must understand how the OR gates work. Right, let me repeat. The OR gate produces a logic 1 when one or more of its inputs are high. A logic 0 is produced only when all of the inputs are low. Now, what does that mean? If one of the inputs is high, therefore if you are using the OR gates, you are going to get the high output. In other words, by inspection, if you see 001 and you are using the OR operator, you must know that the output it's 1, because the OR gates the OR gate produces a logic 1 when one or more of its inputs are high. A logic 0 is produced only when all the inputs are low. Let us look at the truth table. Right, this is the truth table for the OR operator, or I mean for the OR gates. Now, can you see? This is low, high, 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 high. In other words, if one of the inputs is high, if one of the inputs is a 1, know that the output will be high. Right, let us go to the illustration. Now with the illustration, we're going to use the parallel circuit to illustrate this concept. Now if you can just check here, 3 switches labeled A, B and C are used to represent the inputs. And a light bulb labeled X is used to represent the output. An open switch represents a logic 0 and a closed switch represents a logic 1. Right. When the light bulb is on, it represents a logic 1. When the light bulb is on, it represents a logic 1. When it is off, it represents a logic 0. Now, what must happen? The light bulb is on when switch A is closed. In other words, if you can close one of the switches here, the light bulb will be on. Or when switch B is closed, or when switch C is closed. In other words, if you can switch on one of the switches here, the light bulb will be on. Right. What is the Boolean equation? Right. The Boolean equation of the OR gates is this one. It's X is equals to A or B or C. The symbol for an OR gate is a plus sign. It does not mean addition. Let me repeat this. This symbol does not mean addition. Now, how do we read this equation? This equation reads X equals to A equals A or B or C, which simply means that the output of the gate is a logic 1 when A or B or C inputs are in their 1 state. In other words, if one of these gates, if one of the inputs is low, it's high. When one of the inputs is high, know that if you are using the OR gate, the output will be high. In other words, for you to get a high, there must be one high input. The application. Right. The example below shows how an OR gate is used to activate a doorbell from 2 locations. Now the push button at the front door is connected to input A, and the push button at the back door is connected to input B. Right. The output of the gate is connected to the doorbell. Right, this is the doorbell. In other words, this is our output. When either the front door button or the back door button is pressed, listen, when either the front door button or the back door button is pressed, the gate produces a positive signal that activates the bell. Let us try this. Now, I'm trying to push the front door bell, the front door button. Can you see? When I click the front door button, the doorbell rings. Let me go to the back door. In other words, this is an example of this is a very serious example of an OR gate. Alright, now let us end up here. When we come back to our, in our next video, I'm going to show you other gates. Thank you for listening. If you have questions, you have to ask me.